5 of the computer lab, here's what's going on, okay? Suppose we build a new wave pool for Hinsdale Central, okay? And we charge like $5 for admission. All the little kiddies come with the rubber duckies and floaties, and it's totally cool, right? Because you can make waves. Anyone ever been in a wave pool before? You know what I'm talking about? Okay? Yeah, a lot of fun, yeah? In this first case, okay, we have 2 waves, and notice each dot is a foot. So how tall is this wave right here? This wave is how tall? It's 2 feet tall, right? Over here we got another wave, and how many feet tall is it? It's also what? It's also 2 feet tall. Just for the sake of argument, let's call this wave A to make it easier to talk about, and let's make this sucker wave B, okay? And each wave travels towards the other wave at the rate of 1 foot per second. And the way I can tell is, notice, here's wave A, yeah? And at time equals 0, it's at this point in time. But notice 1 second later, what happened to wave A? It shifted over how many dots on the sheet? Like what? Like it shifted over 1 dot, right? And 1 dot is a foot in this case, okay? It's given in the directions there. So notice wave A is moving towards wave B at 1 foot per second, yeah? And wave B is moving which way? It's going to the what? To the left at a rate of what? Also 1 dot per second, yeah? 1 foot per second. So life is pretty easy up until 2 seconds, and then suddenly at 3 seconds, all hell breaks loose. Because what happens, guys? Woo! We have what? We have superposition. Yes, we have what's called wave interference, yeah? In football, you get like illegal interference, right? When one player blocks another player illegally, yeah? Okay? So here we got illegal interference, but it's not illegal. It's just what happens in real life when 2 waves collide. So what's going on here? Okay, and this one is actually done for you up until this point here, and now we want to figure it out. So the trick is, and the reason why I wanted you to have 2 colored pencils, is pick a color for one wave and then another color for another wave, okay? So if you didn't grab 2 colored pencils, go ahead and do that really quick, right at the front there. So what I'm going to do is I'm going to make wave A red. I'll just pick that arbitrarily, okay? So here's wave A. It was here, right? And then it's moving what? 1 dot per second. So notice wave A, it's going to shift over 1 dot per second to the right. Wave B I'm going to make blue, okay? And wave B shifts over 1 dot per second. And notice right here, okay, between these 2 points the waves overlap. So I'm making it dotted there, okay? And I know on your sheet it might have been drawn in solid. A rule of thumb is when the waves start to overlap, try to make it dotted, because in real life, are you going to see wave A and wave B once they collide? No, what you're going to see is the result, the net wave of adding up 2 waves. And what's that rule? Use the principle of what? Position. There we go. We are kind of awake on a Monday morning. Painful, yeah? Okay? So check it out here. Actually, I need some coffee big time. I'm like going through withdrawal. Did I say that out loud? I did. Ignore what I just said. Anyhow, here we go. So what we're going to do is we're just going to add up the waves starting from the left and work our way to the right, okay? Because this is where they start to interfere right here. So notice at this point, wave B, what's its amplitude? What's its height? It's at what? 0, right? Down here. But wave A is at what? At 2. So what's 0 plus 2? Just 2, right? Okay? How about in this middle point right here? Well, this is easy, because in the middle point, each wave is how tall? It's each, what? A foot tall, right? So what's 1 plus 1? 2, right? And then over here, at this point, what's going on here? Well, each wave is, wave B is 2 feet tall, right? Wave A is 0 feet tall, so what's 2 plus 0? 2, right? So in other words, what's happening is as these 2 waves collide, they start to fill in this little valley here with water. Think of that. So it kind of levels off there, okay? How about if I picked a point like halfway in between, like right here? Well, what's going on there, right? Well, wave A then is at 1.5 feet, okay? Wave B in the blue is at half a foot. You see that? So what's 1.5 plus a half? It's what? It's also 2. So in other words, this is actually harder to explain than it is to do. It's a very simple idea that when 2 waves collide, the resultant wave is just the sum of each wave's amplitude at each point. It sounds harder than it really is. You just got to kind of do it there. And in real life, that's what's happening, okay? I know you guys are all like MTV, internet, iPod generation, all that, okay? But what sounds better when you wear 1 headphone or 2 headphones? Woo, 2 headphones, right? Because now you have two waves adding up. They're superimposing on your ears there, yeah? And you can get twice the volume of sound. Plus you get the full stereo sound, which is simulating what you hear in real life with a left ear and a right ear. Kind of makes sense, yeah? Okay? Let's continue. What happens at 4 seconds? Well, you got to keep track of each wave, okay? So wave A is in the red, and it was right here, and it's going to shift to which direction? To the what? Left or right, guys? It's going to the what? To the right, 1 dot, right? So notice now wave A is going to shift over 1 dot, okay? How about wave B? It's going which direction? To the what? To the left, how many feet per second? 1 foot per second. So in other words, it's going to shift over 1 dot per second. Hey, wait a second. What's going on here? What's weird about this? Wave A and wave B are completely what? On top of each other. They're superimposed. You see that? Okay? So if you were wearing headphones, this is where woohoo, the sound is jamming because it's like totally right on top of each other, yeah? Woo, got some tunes grooving there. There you go, yeah? Okay? So how do I know what the final wave looks like? I use which rule? The principle of what? Superposition. There we go. So the resultant wave is simply the sum of each wave's amplitude at each point. Say that like 10 times fast. Resultant wave is the sum of each wave's amplitude at each... Okay, just kidding. Let's just do it, yeah? So we're going to work our way left to right, okay? So at this point right here, how tall is each wave? 0, right? So what's 0 plus 0? 0! Ha! Woo! Okay, how about at this next dot? How tall is each wave? It's 1, right? So what's 1 plus 1? 2. Hey, you guys can count. You guys rock, okay? So that's why this point is here, yeah? How about the next point? Each wave is how tall? 2 feet. What's 2 plus 2? 4. Okay, how about here? 1 plus 1 is what? 2. Okay, and then 0 and 0, 0. So in other words, you never see this red and blue underneath. What are you going to end up seeing? You're going to just see one super honking huge wave, yeah? A 4-foot wave, yeah? Okay? So Alex, if you were in Hinsdale Central's new wave pool here, okay? That's you there. Okay, and you're on a little like rubber ducky here. Quack, quack. Okay? Oops, that's supposed to be rubber duck. Sorry. Okay? Make sure you take a deep breath, and you got to hold on to your swim trunks there so you don't get buried. Okay? Good. What's going to happen at 5 seconds? Can you visualize this? 5 seconds is going to look exactly like who? At 3 seconds. Good job. Because now the waves are starting to pass through each other, but it's exactly the opposite. Okay? It looks the same, but what's happening is wave A now is here in the red. I'm going to do this in the red. Wave A is shifted over how many dots? 1 dot, right? So this is where wave A is now. It's going to look like this. Okay? There we go. And then I'm going to start to make this dotted here because that's going to overlap. This is wave A going to the right. Wave B would have been here, but it shifted over 1 dot. Yeah? And that's where wave B is. I'm going to make this dotted here. It's going this way, yeah? Okay, and again, how do I know what the final wave looks like? I use the principle of who? Superposition, yeah? Okay, so I'm just going to work my way left to right. So at this point, it's only wave B. Same here, all the way up to here. And only when I start here do we overlap, okay? Here, wave A is at 0, wave B is at 2, so the result is 2. Here, wave B is at 1.5, wave A is at 0.5, so the result is 2. Here, each wave is at 1, so 1 plus 1 is 2. This is at 1.5, this is at 0.5, that's 2. This is at 2, that's at 0. So in other words, this is what my final wave looks like. It's the exact mirror opposite of of what was going on at 3 seconds. Okay? The waves are starting to pass through each other. How about at time equals 6 seconds? What does 6 seconds look like? Can you picture this? It's going to look like what? 2 seconds. Ooh, okay. So there's kind of a symmetry in time here. It's kind of like funky. So notice here, wave B moves over another dot. Okay, it's going to look like this. Wave A also moves over another dot. And notice what happened at 6 seconds. Are the waves superimposing each other? Or have they passed through each other? They've passed through each other. Good job. And finally, at time equals 7 seconds, what's 7 seconds going to look like, guys? It's going to look like what? It's going to look like 1 second, exactly. Okay? Except the waves are continuing on their way. Okay? So in other words, wave B is now here. going this way, and put some arrows on because that'll make your life easier so you can keep track of what's going on. Okay? So superposition complicated? The idea is very simple, but figuring out what's going on in real life is a little bit complicated because each wave is moving. You got two thingies moving, yeah? And then each wave has a complex shape. Actually, in this case, we actually simplified it because you're going to see later on when we do our computer lab, you're going to actually plug in a mic, you're going to record tuning forks, and we're going to hit steel poles on the ground, and it's going to sound like you're in some crazy like monastery in Tibet. And then for extra credit, we'll have some of you guys bring in some musical instruments, and you'll see in real life, waveforms are very complex, okay? But the basic idea is superposition, okay? So here's what's nice about part 5 of the computer lab is it simulates what we just saw. And the first thing you do is on these dots, you can grab them, and you can drag out a wave shape, okay? So this would simulate two-foot waves coming at each other, okay? And what's nice is the computer is animating for you what's happening in real life. Woo! There we go. You see that? Kind of cool, yeah? And once it's done animating, you can grab this little red handle here and you can drag this as a slider to help you visualize what's going on. So notice when the two waves collide, the valley becomes filled with the two peaks. And you can tell that this is just a simulation. So I didn't quite draw them the same size. And that's because I'm going through a little caffeine withdrawal here. Oops, did I say that out loud? Ignore what I just said. And then anyhow, the two waves then, A and B, pass through each other and then continue on the merry way. You see that? Okay. This type of interference, do these waves build up or do they cancel out? What do you guys notice here? This is called constructive interference. Bingo, someone was a step ahead, okay? Because the waves are building up. Anybody want to tell me what the opposite of constructive interference would be? It'd be what? Destructive. And that's the second example you're going to do on your own. You guys are flying solo on this one. But instead of a 2-foot wave and another 2-foot wave, here we have a 2-foot wave and a 2-foot trough, -2. What's the result of 2 and -2? It's going to be a big fat what? 0. So you know what's kind of cool? In the Hinsdale Central wave pool, there's going to be a certain spot. You got to pay extra to go here, okay? And it's called the, I don't know, I got to think of a cool name for it. The Zen spot or whatever, okay? If you are right in the middle of these two waves, you know what's really funky? You know what you would feel when these two waves crash? You got a 2-foot crest hitting a 2-foot trough. You know what's going to happen? The 2-foot crest is going to fill that 2-foot trough. Oh, I whiffed, okay? And if I had it exactly the same, you're going to feel what right in the middle? What's +2 and -2 add up to? 0, exactly. Zip, nada, nothing, okay? And you're saying, that's crazy, man. Okay, can a wave really cancel out another wave? And the answer is, yeah, it can, theoretically, okay? You have to have the exact opposite wave, completely out of phase, cancel that out, okay? And what I want to show you guys is a little clip on what's called noise cancellation technology, okay, in a second here. How many of you guys have seen those expensive headphones? I think Bose makes them and a couple other guys do now. Or you can get them for your iPods, okay? And it's supposed to cancel out the outside noise. You know what I'm talking about? Okay? It's based on this simple idea of superposition. The tricky thing is, though, is you have to completely generate the anti-sound, okay, that's coming at you. Is that easy or hard to do? What do you think? Kind of tricky there, right? Okay? So suppose you're in lunch, okay, like Andrew, we're talking, yeah? And let's say, you know, I'm sick of hearing you talk. Okay, no offense there, but I just want to eat my sandwich. Leave me alone. Theoretically, I could have a machine generate the exact opposite of what you're saying to cancel out whatever you're saying there, right? How many of you guys think that'd be a good invention to, like, shut out, like, your little brother or sister, right? Or cancel out your mom. Just kidding. Don't do that. You get in trouble, okay? So let me show you guys